A big hello to all you Flonex users. This is our 9th session, and in this one we will discuss the container components in Flonex. And I'll give you another challenge to expand on the network we are building. So let's get going. The container group in Flonex comprises the accumulator, the container with interface, open container, the reservoir, two-phase tank, and vented container. These components are all connectors or glorified nodes. So they connect straight to the other flow components, like this flow resistance, without a node forming in between them. For this session, I want to focus on the open container, reservoir, and vented container. The others will be handled later within their advanced fields of expertise, but if you are burning with curiosity, you are welcome to check them out in the help manual. The open container represents a dam or some kind of storage vessel that is open to its surroundings. You can set and track the liquid level in the container, and once it fills up, this component will overflow or spill with accompanying loss of mass. On the other side, if it empties out, you can specify whether you want it to act realistically by not having any flow, or you can keep the flow going by enabling a mass source on the component. Further inputs required are the elevation or height of the bottom of the tank, the shape, and its dimensions. And then lastly, we have to specify where our flow component connects to the tank by specification of the height fraction, volume fraction, or actual height. For height fraction, 1 will be at the top and 0 will be at the bottom. And that's the open container in a nutshell. The reservoir component is really just a node with a volume. So there is no level simulation of any kind, but it does require specification of its shape and dimensions to account for real system inertia. And then the vented container, which is basically the same as the open container, apart from the fact that it doesn't allow any overflow. So imagine a float valve on top that will let out air as the tank fills up with water, but closes when full. So there will be no loss of mass, but rather an increase in pressure. And the pressure in the tank will then be determined by the system and not the surroundings anymore. With this, we can now model the Flonex network pond using our open container. The boundary value will now only indicate the temperature with the pressure specified in the component itself. Let's say our pond is dug out to 1 meters in a rectangular shape of 50 square meters and stands half a meter above ground. Say our pipe is connected at ground level, so connected height will be 0.66. And then lastly, our water level in the tank is, say, 20 centimeters above the outlet. So it has a value of 1.2 meters. And now we can solve. The slight change in results is due to the added 20 centimeters of height to the pump inlet that wasn't there in our initial model. But apart from that, everything seems perfect. With all the information I dished out in the past few sessions, you're probably ready to take on the world with Flonex. So I think it's time to put that to the test. I want you to try and add the rest of the hydrogen system to our Flonex network as shown here on the screen. The hydrogen is circulated at 0.18 kilograms per second to cool a generator. So it will take up 50 kilowatts of heat at 2 separate positions where the local pressure drop will be 10 kPa. All pipes have a 3-inch inner diameter with a roughness of 60 microns. The reservoir, which inventory is used to control the system pressure, is kept at 1000 kPa and has a cylindrical volume of 3 cubic meters. And finally, we have to ensure that both cooling lines have an equal amount of flow. Now this is where the challenge lies. Since the pipelines have different lengths, therefore different flow resistances, we have to add resistance to the shorter pipeline using an orifice or valve. So getting all the flows and pressure drops to the exact specified values will take some planning, and the correct use of boundary values, fixed mass flows and other tools you've encountered so far will be imperative. In the next session, I'll show you how I would have taken on this conundrum. Now, don't take any shortcuts and wait for me to show you the way. Go and try this. You'll definitely enjoy this one. And until next time, goodbye.